Hi everyone. Okay, this video is related rates part 2. So we're going to continue by looking at some more examples of related rates problems, but these are problems where you're not going to be provided the equation. So you're going to have to come up with the equation yourself. Okay, but I've still tried to put these into categories to help you out. So our next category is Pythagorean theorem. So these are scenarios that can be represented with right triangles. So the equation that relates the variables would be Pythagorean theorem. All right, here's an example. A ladder 25 feet long is leaning against a vertical wall. So let's draw that. Let's say we have a house, and we have this ladder leaning against the house. It makes a right triangle. Now, the length of the ladder is not changing, okay? The bottom of the ladder is pulled horizontally away from the wall. So the bottom of the ladder is going to be moving away from the wall, and then the top of the ladder is going to be sliding down the wall. But the length of the ladder itself does not change. So we're going to go ahead and label that as 25, which would be the hypotenuse of the right triangle. Now, our other two lengths are changing, so we need to label them with variables, and I'm just going to use x and y. You could use a and b if you wanted to for Pythagorean theorem. Okay, so it says the bottom of the ladder is pulled horizontally away from the wall at a rate of 3 feet per second. So that would actually be dx dt. And that distance would be increasing, so we're going to keep that positive 3 feet per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 15 feet from the wall? So as the ladder slides down, that would be dy dt, which is what we're solving for. That's our unknown. And it says when the bottom of the ladder is 15 feet. So that would be x equals 15. Okay, so our equation is going to be Pythagorean theorem, x squared plus y squared equals 25 squared. Okay, so then you want to find your derivative, and you want to use implicit differentiation with respect to time. Okay, so the derivative of x squared is 2x dx dt plus derivative of y squared is 2y dy dt equals 0, because the derivative of 25 squared is 0. Okay, so now let's see what all we have to plug in. We're solving for dy dt. We know dx dt is 3 feet per second. We know x is 15, but we don't know what y is. Okay, so we're actually going to have to solve for y. So we're going to use Pythagorean theorem again, just to figure out what y is equal to when x is 15. So we'll do 15 squared plus y squared equals 25 squared, and then we'll just work that out. 15 squared is 225. 25 squared is 625. Subtract 225 on each side. And we get y squared equals 400. And then just square root each side. And so we get y equals 20. All right, so we have everything we need to plug in because we've got y is 20, x is 15, dx dt is 3 feet per second, and then we're solving for dy dt. All right, so we get 2 times 15 times 3 plus 2 times 20 times dy over dt equals 0. All right, clean this up. We get 90 plus 40 dy dt equals 0. solve it for dy over dt, so we're going to subtract 90, divide by 40. So we'll get negative 90 over 40, and then we can just reduce that to negative 9 over 4. And again, always include your units of measure, so that would be feet per second. And it makes sense that we got a negative number for our rate of change, because as the top of the ladder slides down the house, that distance would actually be decreasing, okay? All right, let's look at the next example. Now, we are still going to use Pythagorean theorem for this problem. And we're still going to draw a right triangle to model the scenario. But what's a little different in this problem is that we're going to have 3 rates of change. So, let me show you how it works out. 2 cars start moving from the same point. One travels south at 60 miles per hour, and the other travels west at 25 miles per hour. At what rate is the distance between the cars increasing 2 hours later? Okay, so you guys, I'm sure you know your directions, north, south, east, west. So our cars are traveling from the same point, okay? One is traveling south, and the other is traveling west. So we're going to end up with a right triangle like this. So I'm just going to label our sides X, Y, and Z. Z is going to represent the distance between the 2 cars. So all 3 variables are changing in this scenario, okay? All right, so we're going to use Pythagorean theorem to set up our equation, and we're going to go ahead and find our derivative with respect to time. So we're going to get 2x dx dt plus 2y dy dt equals 2z dz dt. All right, now let's think about what we know and can plug in. Well, first of all, at what rate is the distance between the cars increasing? That's dz dt. This is what we're solving for, okay? That's our unknown. Okay, we need to know dx dt. And it tells us that that car is traveling 25 miles per hour. So that's dx dt. The car traveling south, that speed would represent dy dt, and that car is going 60 miles per hour. Okay, now, we also need, though, to know x, y, and z. But even though we're not given those distances, we can figure them out because we're trying to figure out dz dt 2 hours later, okay? So if the car traveling west is going 25 miles per hour, after 2 hours, it will have traveled 50 miles. And the car going south is traveling at 60 miles per hour, so after 2 hours, it will have gone 120 miles. Okay, then we can use Pythagorean theorem to find z. So we'll do 50 squared plus 120 squared equals z squared. All right, so 50 squared is going to be 2,500 plus 120 squared is going to be, I'm thinking of this as 12 squared is 244, and then I have to add 2 zeros, equals z squared. When you add these together, you get this, square root each side, and 269 is actually a perfect square. 13 times 13 is 269, so this ends up equaling 130. Okay, we've got everything we need to plug in. So I'm going to go back to our derivative, and I'm going to plug in 50 for x, 25 for dx dt, 120 for y, 60 for dy dt equals 2 times 130 times dz dt. All right, so basically we're going to clean up the left side. That's going to give us 16,900 equals 260 dz dt. Divide by 260. And that actually works out to 65 miles per hour. All right, so the distance between the two cars is increasing at 65 miles per hour exactly 2 hours later. But again, what I really wanted to give you an example where we had 3 rates of change that were related to each other. Okay, then our last category I'm calling similar triangles because we can represent this scenario with similar triangles. And I like to call this the classic shadow problem. A man 6 feet tall walks at a rate of 5 feet per second away from a light that is 15 feet above the ground. When he is 10 feet from the base of the light, at what rate is the length of his shadow changing? Okay, so let's see if we can draw a picture. We've got this lamp post. Imagine this lamp post. Okay, again, don't laugh at my pictures. And then we have a man who's walking away from the lamp post. So here's where your similar triangles come in. Okay, you could actually represent this with 2 similar right triangles. Okay. All right, now, we know the man is 6 feet tall, and we know the lamppost is 15 feet. And those are constants in this particular problem because those lengths are not changing, okay? The variables that are changing, okay, so number 1, the man is walking away from the light, okay? So he's walking this way. So the distance between the man and the base of the lamppost is changing. So I'm going to label that with X. And as he's walking away from the lamppost, the length of his shadow is changing. Now his shadow would be on the ground right here. Okay, because the light is going to shine down and then create a shadow. That length is also changing. So I'm going to label that as Y. Okay, so we know that the man is walking at a rate of 5 feet per second away from the lamppost. So that would be dx dt. And it would be positive because as he's walking away from the lamp, this distance that we labeled as x would be increasing. Okay? He's getting further from the lamppost. The shadow, the rate at which the shadow is changing, that would be dy dt, and that's actually what we're solving for. Okay? All right, so this is going to take you back to some geometry, but when you have similar triangles or similar figures in general, that means that all their angle measures are the same and the side lengths are proportional. Okay, so the side lengths are not necessarily the same, but they're proportional. So you're going to set up a proportion for your equation. Okay, so we're going to use the ratio comparing the 15 and the 6, the height of the lamppost and the height of the man. So we'll do 15 over 6 equals, now, we're comparing 2 triangles here, okay? we have a bigger triangle where this height is 15, and then we have the smaller triangle where this height is 6. Sometimes it's a little bit easier if you separate the two right triangles. This distance would be y that we labeled. But for the bigger triangle, this distance would be x plus y. Okay? Because basically we're talking about this side, this whole length. Okay? So that would be x plus y. Alright, so when we set up our proportion, we can do 15 over 6 equals x plus y over y. So we're just comparing what we call corresponding sides of the two right triangles. Now, because this is a proportion, we can cross multiply. But to make it easier, we could go ahead and reduce our ratio. So I would reduce the 15 over 6, and we'll get 5 over 2 equals x plus y over y. All right, so we're ready to cross multiply. So we're going to get 5 times y equals 2 times x plus y. And then I would go ahead and distribute the 2. And then we could even combine our like terms or meaning, subtract 2y on each side. And get 3y equals 2x. Okay, so you guys, we haven't really done any calculus yet, but we're getting ready to. 3y equals 2x is basically the equation that relates the variables. So we're ready to differentiate with respect to time. So derivative of 3y is 3 times dy dt. Derivative of 2x is 2 times dx dt. And we know we're solving for dy dt, and we know dx dt is 5, so we're just going to plug that in. And so if we solve for dy dt, we're going to end up with 2 times 5 is 10, but then we would divide by 3. So we're going to get 10 over 3, and always include your unit of measure, so that would be feet per second. All right, so as the man is walking away from the lamppost, the shadow is increasing at a rate of 10 thirds feet per second. But, okay, so those are the examples I have for you for related rates. I feel like I've given you, a good idea of the different types of problems, but please understand these are, not all inclusive, okay? But I would call these like the more popular related rates problems. And we will practice this some more in class. I will see you then. Have a good night.